two identical spacecraft left Earth in the same year, 16 days apart, built from the same blueprints, carrying the same instruments, aimed at the same distant frontier. And for decades, one of them got almost all of the attention. Voyager 1 was the one that went farther, the one that crossed into interstellar space first, the one that became the first human-made object to leave the solar system entirely. But there is something Voyager 2 did that its more famous twin never could and never will be able to. Two things, actually. One of them made in Voyager 2, the only spacecraft in the history of our species to visit 4 entire planets up close. And the other one, quieter, buried in a set of data most people never heard about, is the reason scientists today actually trust what we think we know about the edge of our solar system at all. Because without it, everything we thought Voyager 1 had discovered out there might have just been a fluke. Let's start with the part of this story that's easier to see. In 1977, NASA launched both Voyager spacecraft on a mission that was originally supposed to last about 5 years, aimed at Jupiter and Saturn. But the trajectory each spacecraft was given mattered enormously because it locked in permanently what each one would and would not be able to do for the rest of its existence. Voyager 1 was sent on a path specifically designed to fly close by Saturn's giant moon Titan, one of the most scientifically interesting objects in the outer solar system. That flyby was a priority worth almost any cost because Titan is the only moon in our solar system with a thick atmosphere, and scientists wanted a close look. But getting that close flyby meant bending Voyager 1's trajectory sharply out of the plane in which the planets orbit the Sun. Once that bend happened, Voyager 1 was permanently finished with planetary exploration. There was no way to redirect it toward anything else out there. Its path from that point forward led only outward, away from the solar system entirely. Voyager 2 took a different route. Its trajectory was designed with more flexibility, and because of the specific alignment of the outer planets at that moment in the late 1970s and 1980s, an alignment that happens only once every 175 years, Voyager 2 was positioned to do something no spacecraft before or since has ever done. After completing its own flybys of Jupiter in 1979 and Saturn in 1981, it kept going. And in January of 1986, it became the only spacecraft in history to fly past Uranus, sending back the first and still the only close-up images and data humanity has ever collected from that planet. Then, in August of 1989, it reached Neptune, becoming the only spacecraft ever to fly past that planet as well. To this day, every photograph, every measurement, every piece of direct data we have about Uranus and Neptune from anything other than Earth-based telescopes came from that single spacecraft on that single pass decades ago. Voyager 1 never went anywhere near either of those two planets. It couldn't. Its path was sealed the moment it swung past Titan. Voyager 2 remains, as of today, the only human-made object that has ever visited all 4 gas and ice giants of our solar system in a single continuous mission. That alone would be enough to make Voyager 2 remarkable. But it's not actually the discovery that rewrote our understanding of anything. That part of the story happens decades later at the edge of the solar system, and it starts with a piece of hardware that broke. Back in 1980, as Voyager 1 was making its close flyby of Saturn, something happened to one of its scientific instruments. Its plasma science instrument, a device built specifically to directly measure the speed, density, and temperature of the solar wind, the stream of charged particles constantly flowing outward from the Sun, was damaged during that flyby, and it never recovered. From that point forward, for the rest of Voyager 1's existence, that particular instrument simply stopped sending usable data. Everyone involved with the mission knew it. It became a permanent, accepted limitation of an otherwise remarkably successful spacecraft. Now fast forward to August 25th, 2012. Voyager 1, at a distance of about 121. 6 astronomical units from the Sun, roughly 11 billion miles out, crosses the heliopause, the boundary where the solar wind finally gives out and interstellar space begins. This becomes one of the single biggest headlines in the history of space exploration. Humanity's first spacecraft to leave the solar system. But here's the detail that almost nobody outside the scientific community ever really absorbed. Because Voyager 1's plasma instrument had been broken for over 3 decades by that point, the spacecraft could not directly measure the one thing that would have proven, beyond any doubt, that it had actually crossed into a completely different physical environment. It couldn't measure the sudden jump in plasma density that should occur the instant a spacecraft leaves the heliosphere and enters the far denser plasma of interstellar space. Scientists had to piece the case together indirectly, using other instruments that measured cosmic ray increases and the disappearance of solar wind particles, and by an almost accidental piece of luck, catching a burst of solar activity that let them infer plasma density through a different method entirely. It was enough to convince most of the scientific community, but not everyone. Some researchers pushed back. Some genuinely questioned whether Voyager 1 had crossed into true interstellar space at all, or whether it was still sitting in some strange, unclassified transitional zone the models hadn't accounted for. Without a working plasma instrument, there was no way to settle the argument with certainty. That argument stayed unresolved for 6 years, and then Voyager 2 caught up to the same boundary. On November 5th, 2018, at a distance of about 119 astronomical units from the Sun, slightly closer than where Voyager 1 crossed, Voyager 2 reached the heliopause. And this time, everything was different because Voyager 2's plasma science instrument had never broken. It was still fully functional, 41 years after launch. And the moment Voyager 2 crossed that boundary, its plasma instrument recorded directly, in real time, exactly what theory had predicted should happen at that exact location. A sudden, unmistakable jump in particle density as protons and electrons from the interstellar medium struck the instrument in numbers far higher than anything measured inside the heliosphere. It even measured the temperature of that plasma directly, somewhere between 30,000 and 50,000 degrees Kelvin, considerably hotter than the surrounding interstellar medium overall. A result scientists believe comes from the plasma being compressed as it presses up against the boundary of our solar system from the outside. This is the detail that actually rewrote things, and it's worth sitting with directly. For the first time in the history of our species, we had a direct, unambiguous, instrument-confirmed measurement proving that interstellar plasma really does behave the way physics predicted at the edge of our solar system. Voyager 1's crossing, 6 years earlier, stopped being an educated guess pieced together from indirect evidence and became a confirmed data point, because Voyager 2 had just measured directly the exact phenomenon Voyager 1 could only imply. As NASA's own project scientists put it at the time, without this new data from Voyager 2, there would have been no way to know whether what Voyager 1 detected back in 2012 was actually characteristic of the whole heliosphere, or just a one-off fluke specific to the exact location and moment it happened to cross. And once scientists had two independent confirmed crossings to compare against each other, the differences between them turned out to be almost as interesting as the confirmation itself. Voyager 1's exit from the solar system had been messy. On its way out, it passed through something researchers called a stagnation region, a strange band of space roughly 8.5 astronomical units wide, where the outward flow of solar wind slowed down to almost nothing, sitting right up against the heliopause boundary like water pooling before it finally spills over an edge. Voyager 2's crossing looked cleaner in some ways, but it wasn't simple either. Instead of the same kind of stagnation zone, Voyager 2 passed through a different kind of layer entirely. Oddly enough, almost exactly the same width as the one Voyager 1 had encountered, but built from different underlying physics. Nobody currently has a complete explanation for why two separate crossings, at two different points along the same boundary, would each produce a transitional layer of almost identical width through completely different mechanisms. Then there's the magnetic field. Before either Voyager reached the heliopause, one of the standard predictions was that once a spacecraft crossed into true interstellar space, the direction of the surrounding magnetic field should shift because the Sun's magnetic field and the galaxy's separate magnetic field were assumed to be distinct, independent systems that would simply meet at a clean boundary line. Voyager 1 found that the magnetic field direction did not change as expected when it crossed. At the time, some scientists wondered if that was some kind of anomaly or evidence that Voyager 1 hadn't really left the heliosphere at all. When Voyager 2 crossed 6 years later, its own magnetic field instrument recorded the exact same thing. No significant shift in direction, confirming that what Voyager 1 saw wasn't a fluke or an instrument error. It was real. The magnetic field found in the interstellar region right beyond our solar system runs parallel to the magnetic field inside it, suggesting a much stranger, more connected relationship between our solar system's magnetic environment and the wider galaxies than the old clean boundary model ever accounted for. There is one more strange coincidence buried in this data that scientists still openly admit they cannot fully explain. Voyager 1 and Voyager 2 crossed the heliopause at almost exactly the same distance from the Sun, 121.6 astronomical units versus 119 astronomical units, despite crossing 6 years apart on opposite sides of the solar system during two very different phases of solar activity. One crossing happened during a period of high solar activity, the other during a period when the Sun was comparatively quiet. Given how much solar activity is known to expand and contract the entire heliosphere over time, researchers genuinely expected these two crossing points to look meaningfully different, further apart, or noticeably reshaped by the different conditions. Instead, they landed within a couple of astronomical units of each other. As one of the lead researchers on the Voyager team put it plainly afterward, they simply don't understand why that is. And then there's the leak. Before Voyager 1 crossed the boundary, it passed through tendrils of interstellar particles that had already pushed their way into the heliosphere from outside, like roots pushing through rock, hinting that the border between our solar system and interstellar space isn't a clean wall at all, When Voyager 2 approached its own crossing, it detected something related but distinct, a steady trickle of low-energy particles leaking outward from the heliosphere, extending more than 100 million miles beyond the heliopause itself, well past the boundary line, out into space that was supposed to be untouched by anything from our solar system. Taken together, these findings paint a picture of a boundary that behaves less like a hard, sealed edge and more like a permeable, leaky shoreline, letting material bleed across it in both directions, constantly, in ways the models built before either spacecraft arrived never predicted. None of this would exist as confirmed science if Voyager 2's plasma instrument had failed the same way Voyager 1's did back in 1980. If both spacecraft had crossed the heliopause blind, humanity would still be arguing today about whether we've actually left the solar system at all, relying entirely on indirect inference instead of direct measurement. Instead, because one specific piece of hardware on one specific spacecraft happened to survive 4 decades of continuous operation in deep space, we now have 2 independent, cross-confirmed datasets describing the single, most significant boundary in our entire cosmic neighborhood, and both of them are actively forcing physicists to rebuild parts of the models that came before them. Today, both Voyager 1 and Voyager 2 are still out there, still transmitting, still moving deeper into interstellar space, still the only 2 human-made objects to have ever operated beyond the edge of our own solar system. They are aging. Their power is fading, watt by watt, year after year, and one by one their remaining instruments are being carefully shut down to stretch what little electricity they have left for as long as possible. But of the 2 of them, it is Voyager 2, the spacecraft that never got quite as much attention, that quietly did the 2 things its twin never could. It is the only spacecraft that has ever shown human eyes what Uranus and Neptune actually look like up close. And it is the spacecraft whose functioning instruments turned humanity's first tentative, disputed step into interstellar space into a confirmed, undeniable scientific fact. If stories like this, the quieter half of history that gets rewritten by the machine nobody was watching as closely, are what you come here for, stay close, because there is more waiting at the edge of what we thought we already understood.